In this video, we're going to look at a couple of examples of calculating the posterior distribution. But first, we're going to review the idea of sufficiency because we'll need this a little bit later. So here we have a random sample, which we're assuming depends on a parameter theta, which is unknown. And we have a statistic t, and remember that a statistic is just a function of the data. For example, x bar is a common statistic. T, for example, could be x bar, or s squared, the sample variance, that's a function of the data. And what we want to do is review the idea of a sufficient statistic, as you see there. So a sufficient statistic is one that in some sense captures all of the information about the parameter theta that's contained in the data, right? So again, we have our data here, and we could form any statistic that we want to. But if theta is unknown to us, then we want to try to estimate theta. And so we want to choose the best statistic that will help us in estimating that unknown parameter. So the mathematical definition is what you see here. A statistic t is sufficient for this parameter theta if the conditional distribution of the data, the random sample, given a particular value of little t, does not involve theta. And this is true no matter what little t is, any little t in the range space of big T. So in a sense, the idea is, okay, initially, the distribution of the data just by itself does depend on some parameter theta. But if we want this statistic, capital T, to be this particular value, little t, then that precludes our ability to change theta from then on. So once this statistic capital T is set, then theta must be out of the picture because its value has already been determined. So again, the idea here is that this statistic contains all of the information available in the sample about our parameter theta. And now applying this definition directly can be really difficult sometimes, and so people typically use this factorization theorem, the Neiman factorization theorem, and it gives us an equivalent condition for a statistic to be sufficient. And so the statistic is sufficient if we can take the likelihood function and factor it into a function first that only depends on the data and does not involve theta, and then the other part involves theta but only through the sufficient statistic. And so when we apply this theorem, we're going to want to pay special attention to those parts of the likelihood function which cannot be separated. So let's look at an example. Suppose that our random sample comes from a normal distribution with unknown parameter theta and variance sigma squared, which we'll assume is known. And we're going to define our statistic t to be x bar. And we want to show that this statistic t is sufficient for theta. And that makes sense, right? X bar is what we typically use to estimate the mean for a random sample, which is from a normal distribution. And so it does make sense that x bar would be a sufficient statistic. Let's see why that's true. So first of all, we're going to form the likelihood function. And so notice that we're treating the data as given and theta as the variable. And to get so we start with the form of the PDF of this random vector. And since they're all independent, it's just the product of the PDFs of each xi individually. But again, remember that we're treating the xi's as given and the theta as variable to get this likelihood function. And so the thing to keep in mind at this point is what we want to do is to identify the parts which can be separated and only depend on x, and then the other part will be that part in which the x's and the thetas must both be involved. You can't like that part, this function g represents the parts of the likelihood function that are not separable. So if we take this product, then here we just have a constant here, so that'd be theta to the negative n times this part here. And then remember that the product of a bunch of terms where the base is the same ends up being that base raised to the sum. And then at this point, we would want to expand this binomial squared so that we can try to separate, like I said before, separate as much as we can. So when you're doing this, you want to always try to identify those parts that are not separable. And I think this part here, this middle term, is what's going to not be separable. Like this other piece, I think we can separate that out. And then here, this will only be involved in terms of theta. And then from here, after some simplification, I think you can see the identification of the two functions as indicated here. And notice, as we desire, this function g only involves the data through the statistic t. Therefore, x bar is sufficient for theta. Now what I think would be helpful is for us to review all of the parts that we have encountered thus far and how they lead to the posterior distribution. So we have the conditional distribution as given here, and then we have a prior distribution. We talked a good bit about how to find those. And then if we multiply those two, we get the joint distribution. And then to go from the joint distribution to the marginal distribution of our data, we integrate out theta. And then once we have the joint distribution and the marginal of x, we can form the posterior distribution of theta given the data. And remember that to get that distribution, we will just divide the joint by the marginal. And a useful lemma is that uses this idea of sufficiency is what they call here the sufficiency principle. And so what it tells us is that if we have a sufficient statistic for our parameter theta, then the posterior distribution of theta given the data is equal to the posterior distribution of theta given the sufficient statistic. So let's apply that to an example that we have essentially done before. So I would encourage you to, let's see. In the book, this is given as example 1 on page 127, and I would encourage you to make sure you're comfortable working through all of that. But here we just hit the highlights. So we have here again is our formula for the joint distribution, and then knowing the conditional of x given theta is that normal here, and then theta, the prior, is this normal here, and of course the only unknown here is theta. So then to get that joint, we just multiply those two together. And then as we've done in the past, the next objective would be to complete the square essentially so that we can integrate out the theta. So we can re-express the joint distribution as we see here. And then of course to get the marginal, we integrate out theta like as I said. And then when you get to the actual integration part, you do not have to do that by brute force. You just use your distribution sheet and your knowledge of the normal distribution. And then you can identify that this is similar to a normal distribution with mean A over B and variance tau squared, sigma squared divided by B. And then look at the normalizing constant for the normal distribution, and then that should show you that this integral is equal to this quantity here. And then continue simplifying from there, and we get that the marginal is this expression here. And again, we have seen this sort of thing before a couple of weeks ago. You may want to take a minute and review the video titled Introduction to Bayesian Analysis, I think, or something like that. Now, once we have the marginal, then we can determine the posterior distribution using the formula we alluded to earlier. Now, I went back and got a form of the marginal that involved some of the predefined constants, because using the form that we had of the joint, they cancel, and it's much easier to simplify from there. And so then we get this posterior distribution, and again, this is very similar to something that we did before. I think before, where we have tau squared, now we had a 1, something like that. Again, it's best though if you go through this and make sure you are comfortable with all the steps. Okay, so now let's define a class of densities, which we'll call fancy F. And this is a class of conditional densities, as we see here. And then what we're going to define is what a conjugate family is. So we have another class here, which we're going to call fancy P, and this is a class of prior distributions. This class fancy P is said to be a conjugate family for the family fancy F if the posterior distribution is in the class P, no matter what function we pull from fancy F and fancy P. So in other words, no matter which conditional distribution we select and no matter which prior distribution we select, we're always going to get a posterior distribution that is again in this class. So essentially, the distributions of theta, whether prior or posterior, stay in that family P. All right, so let's look at an example of this. And it's this idea of conjugate families which actually makes Bayesian statistics much easier when we use those families for our priors. So let's look at an example. So let's say we have a random sample, and each one of these comes from a normal distribution where the parameter theta is unknown, as we see there. So essentially we're taking the previous example and we're going to ramp it up a little bit. Now we have a whole sample, and each xi given theta comes from this normal family. There's our conditional. And our prior comes from this normal distribution. Again, x bar. We're going to define a statistic t equal to x bar. And from our knowledge of the sampling distribution, it follows this normal distribution indicated. So using the lemma that we looked at earlier, since we know that x bar is sufficient for theta, then the posterior distribution of theta given our entire sample data is equal to the posterior distribution of theta given x bar. So we really don't have a whole lot of work to do here. We can use our statistic t, and this is really x bar given theta. So let's just treat this as one observation, one conditional observation, and then use what the result we had before here. And so the only difference is where these sigma squareds are, we need to divide by little n. And that is what we have here.